Dr. Ramanathan R. Subramanian. He is working as associate professor in the computer science and engineering department at Indian Institute of Technology, Ropar. He received his PhD in electrical and computer engineering department from National University of Singapore, which is, I think, one of the prominent institute in the world in the year of 2008. So his past affiliation includes Indian Institute of High Performance Computing, which is IHPC Singapore, University of Glasgow, Singapore, Indian IIT Hyderabad, in affiliation of Dr. R. Subramanian. His research actually involves mainly in the area of human-centered computing, and in this particularly extracting and modeling non-verbal behavior signals are used for interactive analytics. So this is something very interesting and very intriguing for me also. And he, Dr. R. Subramanian, is IEEE senior member and a member of ACM and AAAC. So thank you for the session, sir. Thank you for the session, sir, and being with us for this session with us and with our participants. Thank you, sir.
Thank you. So just before I start, maybe if there is a problem with the audio or whatever, I mean, you can never trust the internet when it matters. So maybe I can just give you my number and then I start. So
yes, sir.
It is 8283.
Yes, sir.
053838.
Just minutes. I need to note down, sir. Please say it.
Yeah. So this is what I thought as a backup. So
right, sir.
8283.
Yes, sir.
05. 3838.
Sure, sir. We will be connected.
Okay, so let me start anyway. So
sure,
thanks, Vikram, for the introduction. So the topic of my talk will be utilizing subtle and implicit user behavioral signals for interactive image information retrieval. So I basically come from a image processing computer vision background, and then I kind of started to look at physiological signals. So I'll talk about whatever is in the title over the next one and a half hours. So the outline of my talk will be what I'll first explain to you what I mean by subtle or implicit non-verbal behavioral signals. Then we'll talk about what is called user profiling. That is, you want to estimate or predict a user's emotional state, gender, personality, or the level of cognitive processing, which is what is called cognitive load of the person. So then I'll talk about a computational advertising problem where the task or the objective is to place the most relevant advertisements within a or embed advertisements within a video stream. That is, if you're seeing YouTube videos, you see ads interspersed, right? Presented in the middle. So the question is, how can you present the most relevant ads given the video scenes? That is what is the next problem. And the last one I think is pretty relevant given the times currently. So that is about fake video detection. So I'll talk a bit about that, and hopefully that is all that I'll have time for. So first, let me talk about what I mean by subtle and implicit behavioral signals. So when you talk about user behavioral signals, so we on a daily basis, we convey our intentions, experiences, and feelings, right? And we do this in a variety of ways, right? So you could do this either via explicit signals, so where you consciously convey your state of mind or whatever, and whatever you're conveying is obvious to the outside world. Like when you write it in the form of text, you can express your feelings in the form of text, and that is obvious to whoever is the recipient of your message. Or you could talk it out and then somebody hears what you're saying, right? So these are all situations where you're consciously writing about how you're feeling, and then somebody is able to understand what you're saying. Right. In some other cases, the behavioral signal might not be so explicit. So I call them subtle behavioral signals, but these subtle signals are still conspicuous or obvious to the outside world. So these are signals where the user subconsciously conveys the signal. Like as I'm talking to you, I might kind of um, make some gestures, move my hands, move my body, or move my head, and so on. So I tend to hear some noise at the background. So hopefully, if you can just mute your microphone, that will be better because that's kind of disturbing. So what I'm saying is, uh, as I'm talking to you, I might be moving my hand and making some gestures, and not all these gestures are necessarily conscious. So they may be subconscious, but whatever I'm doing is obvious to anybody who's seeing me. So they are subconsciously conveyed, but the manifestation of these behaviors is kind of obvious to the outside world. So that is what I mean by head and body orientation, facial emotions, kind of behavioral signals. They fall into that category. Then I talk about a third class of behavioral signals, which are called implicit signals, which are basically conveyed subconsciously by the user, and their manifestation is not obvious to the outside world. So here I'm talking about signals such as eye movement. So as we are processing scenes visually, so we make eye movements to understand what is there in front of us. So, but what we are seeing is not necessarily that people will not know about it, right? So that is non-obvious to the outside world. So here I'm talking about signals such as eye movements, brain signals, or signals like ECG. These are biosignals, as we call it, or physiological signals. So basically, I tend to work with signals such as um, the subtle behavioral signals or the implicit behavioral signals. So these are the two main types of behaviors that I'm interested in. And the reason why I'm interested in them is because they are available for free as users perform tasks. So you don't in typical human computer interaction studies. So what they do is they provide users with some technology, and then they see how this technology has improved their lives or whatever uh, via. So they see how these the technology has improved their lives via what are called questionnaires. So the users have to fill up a questionnaire before and after this technology is introduced to them, and then you can compare as to whether this technology has actually made a positive impact. So instead of having to fill out questionnaires, which is an extra effort, and also the fact that you're filling up questionnaires doesn't exactly mean that you're being truthful. Sometimes you can kind of fake your responses in questionnaires as well. So that is what is called the hop-on effect. So your responses might be modulated by the fact that somebody is monitoring it, or the person who is doing the experiment is your friend or whatever. So you want to be nice to people or so what. So it might not be the most objective view. It could be subjective. So what I want to do is with these behavioral signals, these are available for free as users perform tasks. And when you're using non-facial and so these signals are more objective than the questionnaire responses. And the second thing is, when you're using non-facial and non-vocal cues, behavioral cues, you might know that the face and the voice, apart from the finger, they are basically what are called biometrics. So knowing the facial pattern or the speech of a person, or the speech pattern of a person, you can actually recognize who this person is. But when you kind of take all these out of the equation, then figuring out who the person is either impossible or very difficult. So then I can say that the privacy of the individual is preserved. So when you use non-facial or non-vocal cues, they pose minimal privacy concern, and the anonymity of the person is preserved. So that's what I say. So that is why I prefer to work with these implicit and subtle behavioral signals. So what can you get from these signals? So this is the first question, right? So this is one of the slides that I got from Professor Sri Narayanan from University of Southern California. He's one of the pioneers in the field. So you can see that there's a girl who's answering questions, and you can kind of sense where the girl is confident enough of giving an answer, and where there is some uncertainty or some hesitation on the part of the answerer or the girl while answering the question. So this is an educational game where you can actually infer the cognitive state of this person, whether it's confident or uncertain, based on these behavioral signals. So this uncertainty manifests through the combination of vocal. The person might not be so confident answering the question. It can manifest in terms of language. So language is the verbal part. Vocal is when you talk, from the speech, when you remove the verbal part, you just have the vocal intonations and so on. That's what you have. So you just throw away the verbal part of the speech signal. So you're just left with the voice modulations and so on. And you can also use the visual behavioral cues to infer what is the cognitive state of this person. So these are all what are called the non-behavioral, non-verbal behavioral signals. So when I don't use the verbal part of the behavior, I am calling that non-verbal behavior. So using these non-verbal behaviors, the first question is, can you infer things about users? Just like the situation where you can say whether the person looks confident or uncertain. So you're looking at predicting emotional state, the person's gender, personality, and cognitive load. So I'll talk a bit about all of this. So, hello, can you hear me?
Yes, sir. Fine. It's fine, sir.
So typically for most of my problems, I work with emotions. And when you talk of emotions, you will typically tend to talk about emotion categories like happy, sad, angry, and so on. And these are what are called Ekman emotions, because the psychologist named Ekman, he did a lot of pioneering work on emotion recognition and so on. And he found that across cultures, these emotions are exhibited and understood consistently across the world. But for computer based applications, you need not, what I feel is, or based on my experience, what I believe is, you need not have this categorical, you need not predict emotions at the categorical level. Rather, it is enough if you kind of, if you are able to say whether the user is experiencing a positive emotion or a negative emotion. This is what is called valence. And is the user bored or in a bored state, or a highly wakeful state or aroused state? That is what is called intensity of emotion. So these are called valence and arousal. So valence is whether the user is having a positive or the negative emotion, and arousal is all about whether the intensity of the emotion is low or high. So these are supposed to be two independent dimensions, but generally that is what I mean. In practice, you do find some correlations, but as such, they are supposed to be independent dimensions, theoretically speaking. And what you will see is, when you're talking about high valence, high arousal, you're talking about emotions such as excited, delighted, happy, and so on. While you're talking about low valence, high arousal, you're talking about emotions such as angry, tense, frustrated. So those are all situations where you are pretty much wakeful, pretty much aroused, but you are experiencing a negative emotional state. So this is typically what I use for my experiment analysis.
Yes, sir. So there is a question from our participant, says, what is the arousal and intensity of sarcasm in this diagram?
So arousal is basically intensity of the emotion. Sarcasm is one other emotion, which sarcasm is more of a, what to say, it is more of a verbal thing. It need not be necessarily emotional, but sarcasm can be made in it can be comical as well as, what to say, it can be, you can try to upset a person through sarcasm. So it's a separate what to say, it's a separate type of, it's a linguistic type of, I would say it's a linguistic expression, but it need not necessarily, I mean, it is related to emotions in some sense, but it does not categorize as a primary emotion in that sense. So it's not like happy, sad, angry. Sarcasm is a different, it gets a different treatment as such. That's my take on that. So I don't know if that satisfies the whoever asked the question. But
yeah, it's okay, sir. It's
yeah.
done. Yes.
So what we first did was, the first work that I did was in around 2015. So where what we said was, we used what is called the MEG sensor, what is called the magnetoencephalogram sensor, and this is something like, as you are doing tasks, I mean, your brain fires up some signals, and based on these signals, you are able to see what is the emotion of the person. That's the question. Are you able to infer the person's emotion from the brain signal? So here, what you do is you are recognizing the emotion from the MEG, and the advantage of I guess some of you might have looked at EEG sensors. So EEG sensors today come as headsets and so on. So it's like a typical headset that you wear when you're using a laptop or whatever. But MEG is a little more involved. So it's you have to go into a room, and then you sit within the machine, and then the sensor is brought close to your head. The good thing is that unlike EEG, where you typically have a cap or a headset worn by the user, there is hardly any contact between the sensor and the scalp. The contact is very important in the case of EEG, but in the case of MEG, there is hardly much contact between the sensor and the scalp. So it's easier in terms of user experience. The user can behave a little more naturally in that sense. And we also got what is called electrooculogram. EMG is basically muscle movement, and ECG is the heart rate. So with all these biosignals plus the MEG sensing, what we did was showing movie scenes to users. We were able to use the MEG signal to predict whether the movie scene is a positive valence or negative valence, or happy or sad emotion, or and whether it is high or low arousal. So this is what we did. So both valence and arousal predictions were binarized. We say it's either positive or negative valence, and high or low arousal. So this is the kind of binarization or binary classification that we did for this. The good thing about MEG is that with this kind of setup, you get very clean data as compared to EEG, where you might have many issues with the data. It's clean data, but it's intrusive. The problem is that as you go into the MEG sensor, you will have to kind of there's some noise that I hear. I don't know if it's from which person. So if you can please mute. Yeah, thank you. So so what happens is the MEG sensor, you have to remove your ornaments or whatever, and then you just go there without any metallic fittings on your body. And then the other thing is, the room is also kind of electrically shielded, and you're alone in the room and so on. So that's a very unnatural experience for many users. So it is a sort of an intrusive experience, as you call it. The data is very clean, but then the user has a very intrusive experience. So but if you want to do it with many users, user studies like MEG studies are extremely difficult, because the subject preparation itself takes a lot of time, and then you have to do the experiment, and that's a difficult thing to do with many users. So that is why I say it may not be ecologically valid, and if you want to do it with hundreds of users, this may not be the right approach to take. So what we did was, instead of that, we went for what is called the EEG, the simple EEG sensor. So we had a one electrode sensor. So we did what is called a emotional state plus personality trait detection from EEG plus physiological sensing. So this is was in 2017. So compared to the MEG sensor, what you will see is this is much more like a typical workplace kind of environment where the user is wearing some biosensors, and this is the EEG sensor. It's a single electrode EEG, and then he or she watches a movie clip on the PC, and then they kind of rate these movie clips for valence and arousal. Then you can do some analysis between the ratings that the person gave and their cognitive responses. So this is what we could do. So with these commercial sensors, they are much less intrusive than the MEG type of sensors, and they facilitate naturalistic user behavior. But on the other hand, the trade-off is that you have very low signal to noise ratio, whereas MEG is very clean signal. So the challenge here is to use algorithms that can handle unstructured and noisy data in the best. I mean, it can still predict in the presence of unstructured and noisy data. That's what matters in this kind of a scenario. So as long as you have reasonable algorithms that can deal with noise, and suppose your applications require only say 70% accuracy or precision, let's say, so then you can go for the simple EEG kind of sensing, because you can do this for many more users than, let's say, MEG, which is in practice much more difficult to get. So that's what I would say. So this work, so we actually compiled a database called Ascertain, which is connecting the emotional and the personality traits of a user. So people have, I'll talk about this in the next few slides. And what psychologists have seen before is, or observed before is, there is a strong correlation between one's personality and their emotional behavior. So a typical example is, suppose you want to kind of, I mean, I don't know how many of you have seen this. So there used to be a program called MTV Bakra. So what they would do is they'll kind of play a game or whatever. They try to cheat. They try to fool somebody, right?
It's so a prank, sir. Prank. By prank, they're using.
By prank, yeah. You play a prank. So what happens there is that if I were to play a prank, okay, on somebody here, and there are multiple choices for that, multiple candidates. What I will probably do is I'll pick the one who's probably the most emotionally vulnerable. Then I'll try to play a prank on that person. Let's say that I want to kind of spread a rumor that the exams are cancelled tomorrow or what, something like that. Okay, so then the thing is, psychologists have found that that there is a significant correlation between a person's personality and their emotional behavior. So this personality emotional behavior has been studied by many psychologists, and one such psychologist was this gentleman called Eysenck, and he said there is a strong correlation between personality and emotional behavior. And the general, there are many theories on personality dimensions or personality traits, but the most common personality model, or the most popular one currently, is what is called the ocean personality model, where we are characterizing a person's personality based on 5 dimensions. One is called openness, which is whether you are curious or you're open to new experiences, or you're cautious. Conscientiousness, which is basically about how dutiful or how easygoing you are. Extraversion, which is all about whether you're talkative or reserved. Agreeableness is whether you're compassionate or dispassionate. And neuroticism is the one that I was talking about in the example before. Are you emotionally stable or you are nervous? So that these are the 5 personality dimensions that are used to characterize a given person. So what Eysenck did was he posited that extraversion is accompanied by low arousal, which means you have to kind of really excite extroverts so that they are in an excited state. That is, extroverts require more external stimulation than introverts. While in the case of neurotics, they are more sensitive to external stimulation. That is, like I said, in cases where you would want to play a prank on somebody, you would do it with a emotionally vulnerable person. So neurotics are more sensitive to external stimulation and are easily upset and nervous due to minor stresses, while emotionally stable people are not so sensitive. So this certain database basically analyzes the relationship between emotional behavior and personality traits, and then this emotional behavior was measured via the sensors that I was showing you in the couple of slides before. That is, they are minimally invasive, wearable, and low-cost sensors. That's most important. So what we had was, from the users, we acquired emotional self-ratings. That is ECG, EEG, GSR, and facial movements when they watched 58. So when 58 users watched 36 movie clips, and then we use this for our study. So the main takeaways, or the main inferences from the study was that when you look at the same type of stimuli, that is, when you look at emotionally similar movie clips, then people with different personality traits tend to react differently. So the user responses to similar emotionally similar clips, they characterize personality differences, and the correlations between the personality dimensions and the physiological or the biosignals that we captured, that was better described non-linearly than via linear relationships. And the low-cost commercial sensors, the problem with them is that they are usually error-prone. As I said, they have low SNR, but with careful experimental design and enough data, you can still have meaningful relationships. So what we achieved was both above chance recognition of both the emotional traits, that is arousal and valence dimensions, as well as the personality traits. So this is what we obtained from this certain data set. So similarly, you can also kind of, in another study, we tried to predict the user gender, and we showed images, face images to users. So what we tried to predict here was, what is the gender of the user who's seeing these images, and what is the balance of the uh, face image that the user is seeing. So the user sees an emotional face. So what is the balance of the face that is being seen, whether it's a positive emotion or a negative emotion. So this is what we studied. So here what we did was, we had 28 users participating in the study. So we had 14 male and 14 female who viewed emotional face images. So the question is, can we employ eye movement and EEG based cues to predict the user gender and the emotions of the displayed faces? So these are the stimuli. So you want to get the stimuli emotion and the user gender. The user is the one who's watching this stimulus. So here what we do is, the user basically sees a emotional face. So user views a stream of emotional faces. The eye movements and EEG signals are recorded during the viewing task. So from the recorded signals, what you want to do is, you want to predict the user gender, whether the user is male or a female. And you also want to predict whether the displayed face exhibited a positive or a negative emotion. So the main motivation for doing this is, like when you play games, I mean, most people play online games now, right? So based on certain physiological signals or whatever that they exhibit when they are playing a game, the question was whether you can predict their gender. And if you can do that, I mean, without having a camera that is recording the person's face or whatever, if you can actually, let's say even with 75 to 80% accuracy, if you're able to kind of predict the user's gender, then you can show ads, fashion ads maybe, to the user. And the more accurately you can predict, the more relevant ads you can show to the user. So you don't ask the user explicitly whether you are you a male or a female, but you are able to predict that automatically, and then present the relevant ads to the user. So that could be a nice way of generating revenue, right? So that is the whole point here. So what we did was, here we use what is called the RAFD dataset. This is a very famous dataset in terms of emotional studies. It's called Rathbone face dataset, and then we use the different emotions, the Ekman emotions. There are 6 Ekman emotions plus neutral. So we showed both the full emotional phases plus the masked emotional phases. So we actually covered either the eye or the mouth region in this case. So we would ask, we'll show this emotional phase for 4 seconds to the user, and then we give the user 30 seconds to determine what is the emotion that is shown in the face, and then we will do 288 trials like this. So 288 faces are shown, out of which 144 are full faces and 144 are masked faces. So you have 24 models from this RAFD dataset, and then you have 6 emotions, 6 Ekman emotions, and 2 intensities, high or low. So in 2 sessions of 144 stimuli each. So what you are doing is you are the 2 sessions correspond to the mask and the no mask condition. You are showing a fixation for half a second, a stimuli for 4 seconds, and then the response time for the user to make a decision on the emotion that is presented or the recognized emotion is 30 seconds. So this is the protocol basically. So what we found was that female users recognize the facial emotions both faster and more accurately, especially negative emotions. So a lot of studies, and even earlier they had found that females are especially sensitive towards negative emotions. They can quickly sense these negative emotions from others. So this was actually repeated in our study as well. So we found the same result, and whether this emotion was mild or high, even then female sensitivity was higher than male sensitivity, and high intensity emotions were recognized much more accurately than low intensity emotions. And happy was the easiest emotion to recognize, while fear is the most difficult. So this is basically what we got from their explicit responses. So we asked, like I said, each user was asked to recognize the facial emotion within 30 seconds of time, and based on these responses, which we called explicit responses, we found these results. Now, then we looked at the EEG responses of the users. Now, instead of just looking at the EEG signals, applying a classifier, and then saying that, okay, we are able to do gender recognition with 90% accuracy. So what we wanted to see was whether there indeed exists some signature in the neural signals of male and female user that is gender specific. That is what we wanted to see. And what we found was, so for people who don't know about ERPs, I'll just briefly explain what that is. ERP is what is called a event related potential, which means from a young age, let's say for an example, from young age we are used to looking at faces. So as soon as we see a face, there is some processing that happens in the brain, and actually there is something called an ERP that fires up in the brain. So that's what is called the P300 or whatever. So immediately after you recognize a stimulus, within 300 milliseconds, you are actually there is a signal that fires up in the brain. So that is what is called the event-related potential. So they are measured relative to some event presentation. So in the case of ERP signals, what we found was these ERP amplitudes were higher for females for the negative emotions. The negative emotions are basically the red colored curves here. So what you see is for females, it's at the O1 electrode. O1 is the name of an electrode in the, in the headset that we use. O1 is one of the electrodes. And for females, you see that the amplitudes of the red curves are higher than the blue curves. The blue curves are for males, right? So we saw higher ERP amplitudes for females as compared to males. And for males, what we found was the blue curves are the male curves. And we found that the latency of these ERPs was lower for positive emotions. The positive emotions are the blue ones. So those are lower for males as compared to negative emotions. So M this is an electrode called O2. So this is for O1 for females and O2 for males. So we found higher ERP amplitudes for females for negative emotions and lower latencies for males for the positive emotions. So this is what were the main findings from the ERPs. So stronger N100, as we call it, 100 is the latency post the presentation of the face. Stronger N100 and P300 peaks in the negative female ERPs for both the high intensity as well as the low intensity emotions, and lower latency for the male ERPs. So this is what we found. And using a CNN based architecture, what we gathered from the EEG data is we can actually do greater than 93% AUC score. We can recognize the user gender correctly. That is for the high intensity emotions, for the very obvious emotions where you see the emotion really peaking. That is what I mean by high intensity. Like you can smile very mildly, or you can really laugh, right? So I'm talking about when I talk about high intensity emotion, I'm talking about a laugh kind of an expression, while low intensity is more of a smile. So based on user responses to the high intensity or low intensity emotions, using from the EEG signal and using a CNN architecture, we were able to get greater than 93% AUC score for gender recognition, and this was correspondingly 88% for the low intensity emotions. And when it came to the recognizing the emotion of the viewed face, emotion face, that the balance of the emotional face was better characterized by the eye data rather than the EEG data. So the eye data was more discriminative of the facial emotion and the stimulus as compared to the EEG signal. So this is what we found. So just to summarize the study, so this was basically motivated by prior studies which observed that females are faster and more accurate at recognizing especially negative emotions, and our explicit user responses were consistent with the previous findings. ERP show gender specific differences between males and females while processing emotional faces, and the classification experiments confirm that EEG signals encode gender specific information better, while eye movements better convey balance related information, that is the emotion of the presented face. So that's what I mean here. So then there's this last thing about cognitive load. So today we talk about this thing called big data, right, where data has many attributes and so on. So when you have huge data, that is data with many dimensions, we still need to sense snake from multi-dimensional data, right? But when you want to illustrate or plot the data, you can only plot data up to 3 or 4 dimensions, right? You can just use the 3D model or a dynamic 3D model to visualize data. But when it comes to big data which have many dimensions, you probably see the need for more creative and intuitive visualizations. And more than that, you don't necessarily have physically able users everywhere. It is also important to cater to the visually challenged community. There are about 253 million visually challenged people in this world. So you might want to kind of make these visualizations more user friendly, or what to say, accessible. That's the correct word. So the visualizations have been should be accessible to a large community of users, and that's why we need to explore alternate modalities for visualization, including auditory, tactile, gustatory, and olfactory. So these are about sound, touch, taste, and smell. So in this case, I don't know if you are able to hear the audio, but what we said was this is an astronomical image. So where you are kind of focusing a star with different levels of focus. You're capturing a star with different levels of focus, And this level of focus is conveyed via 4 parameters. One is, these are acoustic parameters. That is, one is called roughness. I don't know if you're able to hear it, but there is, it's important that you know what this is. So you are trying to convey this focus of the image via 4 acoustic parameters: roughness, noise, which is your sare gamma. So that is the frequency. And we combine both roughness and noise. This is what it is. So if you have the 10 levels of focus, then you can convey this using the C major scale, sare gamma pada nisa. So this is
Yes, sir. We are getting, I mean, very slight audio.
yeah, I think if you
Yes.
increase the audio at your end, it might be even better.
Yes.
So
Yes,
I
sir.
don't know if you can do that. So yeah, my audio is at 100%. That's why I can't do it anymore. So you might have it. So I'll just play it for the benefit of just a minute. So as you see that the focus is becoming better and better, you go to higher and higher frequencies. I guess you get the idea. So what we did was, we wanted to figure out which of these acoustic parameters are easier to understand for the average user. So what we did was, we use 6 visualization types. That is, we use the image as such. We use the 4 audio parameters that I showed you in the previous slide, and we also used one presentation style, which is where we showed both the visual image as well as the combined audio stimulus. That is, combined is basically roughness plus I think it's roughness plus pitch or whatever. So one of those. So it's roughness plus noise. So we combined all of them in one of the situations, right? So users, are you able to see what I'm my screen still? Hello? Hello?
Yeah, I
Hello?
think we have lost this sharing screen.
Okay, 1 minute.
Yes,
So
it's dropped actually.
yeah. So let me just go.
Yes.
So we had 2 sessions consisting these 6 visualization blocks. User, the users now had to do was, they had to determine or predict the focus level of the image corresponding to the stimulus that is presented. So I may present the audio stimulus or the visual stimulus, and then the user has to say that this is focus level 1 to focus level 10. They have to make a choice. So we did 2 sessions basically. One is where we asked the user to immediately estimate what is the focus level, which is what I call as immediate recall. And in the second one, we asked the user to say, press the enter button when you hear or hear the signal corresponding to focus level 5. So that is what we call as the compared recall session. So we had 2 types of recall from the user, where one is where they had to immediately say this is focus level 5 or focus level 4 or whatever. The other session, we explicitly said you have to concentrate or look out for focus level 6, and then they had to press the enter button whenever the stimulus corresponded to focus level 6. I hope the difference is kind of clear to you. So at the end of each block, we actually captured their or recorded their explicit cognitive load impressions using what is called the NASA TLX parameter. So then the task was to correlate these explicit user impressions to their EEG responses, which are the implicit impressions. So the main findings from this study was that we saw significant correlations between trials labeled as high or low cognitive load by users, and the sound data mapping accuracy, which means when an acoustic parameter was known to induce low cognitive load, which is I'm not getting stressed much in the process of estimating what is the focus level from the stimulus that is presented. That is what I call as a low cognitive load parameter. So what we say is, when a acoustic parameter induces low cognitive load or minimum confusion or minimum effort in the user, that is most easy to understand, which means the mapping accuracy from the sound to the actual focus level, the data that it conveys, is highest. So parameters that are low cognitive load are easy to understand. That is the simple way of interpreting this result. So visual and combined were the best visual and auditory parameters. So this is what we found. So when you either showed the images as such, or when you played the combined audio signal, that roughness plus noise, so that was actually the best parameter that conveyed the focus level. So, and the second thing was ERP amplitudes were higher for the compared recall task as compared to the immediate recall task, and more user attention. This meant that more user attention was required for the compared recall task. And if you have worked with EEG signals, you might have known that there are different frequency bands in the EEG signal. So one of them is called alpha band, or what is called the meditation band, which means you are exhibiting calmness, or you are in a state of you're in a relaxed or a meditative state, you will see high alpha power. So that means when you have when the signal induces low cognitive load, that will correspond to high alpha power, and that alpha power was highest for the most intuitive parameters, auditory or visual parameters. That what we found. Upon categorizing parameters as either high or low cognitive load inducing, based on the user responses, we actually got 64% cognitive level estimation accuracy achieved with 5-fold cross validation using a CNN approach. So using a CNN architecture, we were able to automatically deduce the cognitive load that is induced from the EEG signal. So this is what we did in this study. So now I'll talk about another interesting application, which is what is called computational advertising. So here, your task is, first of all, are you able to infer the emotion that is conveyed by an ad, whether the ad is a positive ad or a negative ad, or positive ads are typically promotional ads, while negative ads might convey something like anti-smoking or whatever. So ads can either be positive or negative emotional, and also the emotional intensity. So you wanted to characterize any ad in terms of valence and arousal, and given a video stream, you wanted to use this emotional similarity between ads and the video scenes to embed ads at appropriate places in the video stream. So this was the basic objective. Now, if you want to ask the question as to why we need to decode ad emotions, the answer is that basically emotion works very well in advertising. That is what people have found over years of studies. Like when you kind of appeal to viewers based on emotions, that is when you make the maximum profits. This is what advertising studies have shown. When you kind of just appeal to the rational sense, the audience is rational, then it is the campaign effectiveness or the profit gains are much lower, 16%. While if you appeal to both the rational as well as the emotional sense of the viewer, you get somewhere in between. So basically, emotional ads, they are received best by the users. This is what advertising studies have found, right? So, and what you should also know is that by 2020, the estimate is that uh, emotion detection and recognition market for ads is actually projected to be worth $22.65 billion. So there's a lot of interest in Western countries and even places like India as to how users uh, respond to a given ad. Is the response in terms of, I mean, is the response on expected lines, or is the ad as effective as we designed it to be? These are all questions that advertisers they're always asking. So especially in the US, this is a very serious topic of study. So this is what I wanted to say. So here we had both the promotional ads. So you can see even from the appearance that two of the ads are kind of negative ads, and two of the kind ads are basically positive ads. So we use both the message ads as well as the promotional ads in the study. And the first task was to see how you can look at the content as well as the user responses. So again, we looked at EEG as users watch these ads. So we use the audio and the visual cues from the ads plus the user responses to these ads to kind of classify each ad to be of certain valence and arousal. Here, the valence and arousal are basically binary classification tasks. So you say an ad is high valence, high arousal, or low valence, high arousal, or whatever. So you have to place an ad within one of the quadrants in the valence arousal plane. This is what we wanted to do. So we explored this task in both the content and the user-centric, using the content and the user-centric approaches. And for the content-centric approach, what we looked at was how can you characterize the ad in terms of visual features. So for that, what we did was we used what is called the places dataset, because here you have many images that are captured with different perspective, different lighting, and at different times of the day. So the capture is very varied. And then from there, I mean, and typically these are also the cues that are used by directors to convey the emotion in a scene. So typically the sad ads or the negative ads are typically captured under dim light or whatever. So based on these cues, the visual cues, we try to compute what is the valence and arousal of an ad. And for we also used audio. So for audio, we used what is called a spectrogram feature. And spectrogram basically tells you what is the intensity of different frequencies in the audio signal. So if you look at low arousal audio, that is something like a symphony kind of an audio or whatever, you will find that the low frequency components have significant intensity. That is, the intensity is basically given by whether it is green or blue or yellow or red. So this shade tells you how much is the intensity of a given frequency. So the low frequency components are having high intensity in a symphony kind of a situation, while if you are having a very intense scene like somebody shouting or whatever, then you also have you see that the intensity of all the or most frequencies in the spectrum, they have high intensity. So you see that the red shade is now seen for pretty much all the frequencies in the spectrum. So that is why spectrograms can also tell you something about the emotion in the scene. So what we found was we looked at, as I said, we looked at both the content and the user-centered cues. So with the content-centered cues, we found that the visual cue was more effective. So using the visual features and what is called a multitasking algorithm, we got 94% F1 score and 96% F1 score. This is for valence, it's 96, and for arousal, it is 94% on a set of 100 ads, basically. And when we used EEG, we found that we actually got slightly better results as compared to the content-centered results. So here we got 97% for valence and 96% for arousal. And the plausible reason is that the user knows the emotion best, because like you have things like satire and so on, like somebody had pointed out earlier. So these may not be very well captured by the content-centered cues, but we user as humans, we are able to understand the context, the emotional context best, and then we are understanding the emotion in the scene in the best possible manner than any other than what is conveyed by the music or the visual content of the scene. So that is why what we found was that the EEG signals actually gave us the best result for both valence and arousal prediction. So the last thing that I will talk about is deepfake detection, which is kind of very relevant in today's world. So you might have known about fake video creation. So one of the examples is this.
Sir, do I need to play the video? I mean, that video we have planned.
No. As long as are you able to hear the audio now?
Not yet, sir, actually. Not in a identifiable manner.
Okay. That's fine. So here you see Obama talking, right? Now you can play the other video. Play the other video.
Okay, sir. So let me share. And with audio, yeah.
Democracy is a fragile thing, more fragile than you want to believe. If the election fails, there is no democracy. I don't have to do anything. You're doing it to yourselves. People are divided. Your voting districts are manipulated. Voting locations are closing, so millions can't vote. It's not hard for democracy to collapse. All you have to do is nothing.
So this is basically one of those videos that was posted by a senator on social networking website. So that was for the US election. So we know what's happening in the US election now, right? So this is a recent video, and yeah. So so this is obviously a fake video. So let's go back. So the question is, when we see these videos, we kind of we have a strong feeling that these videos are fake. And these videos have both the visual channel as well as the auditory channel, right? So the question is, how are we able to? So played the video, you probably saw some graph that is going on, and just to show you the graph, this graph actually plots. What is the distance between the audio and the visual channels for a given video, which means when it's a genuine video, you kind of know that the audio and the visual channels, they should tie well. That is, they come from the same source, right? So somebody makes, I'm talking, so I'm making some lip movements as well as I'm kind of my voice is heard. So the audio and the visual sources are tied together. While if I have to make a synthetic video like the one that we are seeing, then you have to kind of make the lip movement synthetically and then also add this audio synthetically, right? In most cases. So you will see that there is greater dissimilarity between the audio and the visual channels. So what you see on the right is basically this graph computes the distance between the audio and the visual channels, and that should be higher for a fake video while it is lower for a genuine video. So this is basically the idea. So if you see that, so this is a fake video, and you see a high dissimilarity score indicating that the video is manipulated. That's what I wanted to convey. So for this, again, we employed both the content and the video-based analytics. So for the content-based method, what we did was we cut the video into 1 second segments, where we for 1 second will have about 30 frames, right? So 30 FPS video. So we had the sequence of frames. So within each frame, we would just look at the face, and then we would try to kind of get a representation of the facial region using a CNN, convolutional neural network. And then for the audio, we will again compute the spectrogram representation, or here it's the MFCC features, and then feed this spectrogram into a audio CNN. And then basically what you're looking at is how close or how far apart are they in the feature space, the video and the audio. So that is what our model will learn, or the neural network architecture will learn. So the objective of this neural network is to give out a small distance between the video or the visual and the audio channel if the video is genuine, and a high distance between the visual and the audio channel if the video is a fake video or a manipulated video. So that's what I've put here in terms of the mathematics. So we considered 1 second segments, and then visual as well as audio segments. And just to give you a flavor of what is there, if the video is real, you have a label of yi is equal to 1, and if the video is fake, you have a label yi is equal to 0. So if you know about loss functions, you're typically using neural networks to minimize the loss during training, and this loss function L1 will be minimum. If yi is 1, then you want to have dit, which is basically the distance between the video and audio channels, to be minimum. So this, when yi is 1, or for a genuine video, you want the distance between the video and audio channels to be minimum, while for a fake video where this yi is 0, so which means this term becomes 1, you want this margin minus dit to be equal to as close to 0 as possible, which means you will learn a margin, or you will learn a dit which is at least as high as the hyperparameter margin. So this margin is something that you said, it's a hyperparameter, and let's say it's equal to 1. You need the dit to be at least equal to 1 in order to minimize this contrastive loss. So this is what is called the contrastive loss, where you kind of contrast the visual and the audio channels in the video. So this is basically the idea. So for genuine videos, your model should output a low audio visual distance, while for manipulated or doctored videos, it should output a high distance between the visual and audio channels. So the other thing was that we also looked at the eye movement patterns for these videos. So this is a real video. So if you see, what we asked users to do was, we asked them to simply watch these videos and label the video as either real or fake. So the typical behavior is that as users, when they don't know whether the video is real or fake, they'll try to first figure out if there is something that is unnatural in the video. So they will try to kind of go around the scene and look for where possible or candidate regions where they think there's some manipulation, right? But when you actually see a manipulation in the video, when it is obvious, then you will actually try to verify whether this manipulation that you've discovered is actually existing or not. That is, you want to do the verification task rather than an exploration task. So this is what we call it as exploratory versus explanatory viewing. That is, in the case where you have a real video, the left-hand side is a real video. So you can see some, these are basically what are called gaze heat maps. So you can see the heat maps on the person who's talking, then the person who's the onlooker, as we call it. So the other person in the conversation, and also some other characters in the scene. So you can see this gaze map being spread around the scene. While the right side, you actually have a doctored video where the mouth of this person is manipulated. So once you show that to the user, you will see that there is pretty much the gaze is localized on the face and not on the other people in the scene, right? So because they sense that there is something that is unnatural in the character's movements, the lip movements, and so on. So most of the gaze is or visual resources are spent in verifying that the manipulation is indeed there. So you kind of compare that region with the neighborhood and then verify if your discovery is indeed true or not. So that is what is happening in the right video. So that is why we call that when there are the scene is natural, we see more of the exploratory viewing behavior, while for the right video where it is manipulated, we see more of explanatory viewing. That is, in the real videos, you have diffuse gaze, while in the fake video, you have more of focused gaze on the manipulated part. And this is in terms of the eye movements. We also use some the EEG signals. So in EEG, I've talked about ERP, right? Event related potential. There's also one of the ERPs that you can tend to see is what is called the error related negativity, which means when we do a task, when we know that we have committed a mistake, or when we are presented with information, we know that something is wrong with the information, you kind of consciously sense this, right? But even before you consciously sense this, there is some neural signal that fires up. That is called what is called the error related negativity. And what we found was that because the manipulated videos had this error, that actually gave rise to what is called the error related negativity signal in the EEG in the EEG waveform. So this ERN was kind of typically seen for multiple electrodes in the for the fake videos. So this is what we saw, and we also got greater than chance accuracy towards detecting whether the video is real or fake just with the EEG or the eye movement patterns. That is the information gathered from the users. And but this accuracy was much more with the content based cues in this case, because here it is not about emotions, but it is about whether the content is kind of genuine or fake. So there's the task is more objective here. So you are looking at whether the video statistics are true, or there is something that is there is an artifact that is different from the rest. So here the content based method works much better than the user based method, while for the computational advertising problem, we found that the EEG was more informative as to inferring which what is the emotion of the ad. So this is basically what I wanted to convey. So basically this is what this kind of ends my presentation, and you can ask me any questions if you have. So that is what I want.
Yeah. So thank you for the talk, sir. So now this forum is open for the questions. I request participants to raise their questions. They can enable their audio and raise the question. So we have got few questions in the chat box also. There are one question from the participants, like is there any labeled data set for fake media identification? So
yeah, so we actually used two data sets. There's something called DFDC. So it's a deep fake detection challenge.
okay.
You might have known about Kaggle. So
yes,
Kaggle is a data science challenge. So DFDC is part of this Kaggle challenge data set. And we also had for the user study, we used what is called a Google deepfake detection data set. So this is this is what we use for. I mean, you can look at my papers; they will have the descriptions better. But there
yes.
are multiple labeled data sets for deepfake detection. For audio, will the RNN work? So what you could use RNN, but typically what I would do is when there is RNN is good in terms of knowing how a phenomenon evolves. So basically RNN, what you're doing is CNN can capture spatial relationships well, while RNN does this over temporal patterns. So
Yeah.
you are extending encoding of what you call redundancies, both spatially as well as temporally. So you're learning spatio-temporal patterns, basically. That's what you're doing with RNN. So RNN you could try, but we use what is called 3D CNNs. So we use 3D CNN for both the audio and the video. I am unable to give you what is the performance of the RNN for this task because we didn't use the RNN, but RNN has typically been used for emotion recognition. That much something that I know, because emotions evolve over time, and you might in some cases get better the temporal signal might actually give you the a better hang of the emotion, basically. So it has been used for emotion studies. That's what I can tell you. So Niranjan Nayak says, do the same algorithm is used in EEG and EMG machine. So I don't get what he means, but ECG and EMG are both biosignals, and then you have specific algorithms for processing these signals. So typically what you do is, from what I know,
Good afternoon.
Yeah, I think participant is raising the question. Yes, please
yeah,
go ahead.
Hello.
Yes,
yeah,
yes, please go ahead.
Sir, actually, in EEG machines, you have to use the algorithm. The same algorithm is used in ECG and EMG machine. I asked this question.
no, they have slightly different methods of processing methods, simply because the EEG uh, is much more dense as compared to the other biological signals, I guess. I mean, your heart rate is like 64 beats per minute, while your EEG, you typically get 128 samples per second. So the processing methods for these two, they vary vastly from whatever I know.
Right, sir. So the question may be partially answered. So we have done with the question which are posted in the chat box. So now I have one particular question, sir. Like the slide it has been pointed out that this personality and behavior are related. I mean, they are having this correlation.
Yeah.
Now, suppose I am working in a system, information retrieval system, which are dealing with the text data or text kind of details. So we are getting few personality information from the user's profile or maybe some other source, and we are getting some information about his behavior on the information. So, I mean, can you tell me tentatively how I can correlate these two aspects to get a personalized information retrieval system, sir?
I'm not able to directly answer your question because I haven't done the study myself. So
Yes,
my study was more whether your emotional responses are.
yes, sir. Please. We are getting some interpretation, some internal. So, Niranjan, I mean, do you want
Hello,
to?
can you hear
Yeah.
me?
Yes, Niranjan Nayak is. I mean, I think wants to raise something. Okay, let me mute. Then only we can discuss. Yes, sir. Please go ahead, sir. Yes, sir. Please. Sir, please go ahead.
So you're asking me, okay.
Yes, yes.
So what I'm saying is that you might have heard about this Facebook scandal recently, and they passed this data to something called Cambridge Analytica. You might have heard the name.
Yes,
So
yes, sir.
that played a great role in Trump winning the last US elections.
Right.
Unfortunately, I think he's losing this time. So, but what I know is that this Cambridge Analytica basically used Facebook posts and so on to infer the personality type of each user. So they kind of use the textual cues to figure out what is the personality of each user. And that way, what they did was they actually sent out personalized messages to different types of users. Like one type of user was shown positive messages, while another type of user was always shown negative messages. So that way they were able to kind of manipulate users to vote for Trump. So this is what I know from messages
Yes,
on
yes.
internet and a documentary and whatever. So this has typically been used for personalized information presentation. So that's what I'm telling you.
Yes, yes. So I think we are getting a lot of tools based on these backgrounds, like Grammarly is now getting used. I mean, this kind of inference that what is the tendency of your writing. I mean, I think we are now getting these kind of similar tools on different platforms.
Yeah.
So so I think with this we can share our greetings to you about this extensive detailing during the session related to beyond visual signals or beyond visual cues. So thank you for that, sir. We will be connecting to you for the upcoming sessions, upcoming events also at IIT Kurukshetra, because we are living in the adjacent state. I mean, it was coincidentally happened that we are approach you for this FDP. So this is, I think, this is the first time in IIT Kurukshetra we are having experts from IIT Ropar in computer science department at least.
Okay.
So it was, yeah. So I have shared this fact with our HOD also because HOD sir's daughter is still in IIT Ropar. She's a student of, I think, fourth year. So it was just happened during the discussion of one of the informal discussions. So thank you for being with us for this FDP and for this session, sir. And on the behalf of participants also, I want to share my greetings. Thank you very much, sir.
Thank you so much. Yeah, thanks. Good day to all of you. Thank you.
Yes, sir. Thank you, sir.
Okay.
So I think with this, we can conclude this session, and we will be connecting for the tomorrow sessions. And tomorrow onwards, we will be starting the discussion on machine learning or machine intelligence techniques. So tomorrow we will have first two sessions on machine learning techniques and how these techniques are specifically used for information search or information retrieval related applications.